Hello and welcome to the video. And in this video, we will discuss negative feedback amplifier with parasitic poles and zeros. And then we will discuss the delay introduced by the parasitic effect. So as we have discussed earlier, so while realizing op-amp at block level, so basically we required to sense the input or basically the difference between the actual and the desired speed, and then accordingly we were integrating that speed. So then we come up with a solution that we have two integrating elements, capacitor and inductor, and we discussed why we neglected or ignored inductor. So basically we have a capacitor and we need to integrate a current, and we have uh, difference voltage. So let's say we have a difference voltage, let's say between VA and VB. So when based on this voltage, we have a voltage controlled current source, and based on this voltage, it will produce a current of Gm times voltage difference, where this current source has a transconductance of Gm, and this current is basically passed through a capacitor to integrate the current, and thus we get this value as output as a integrated form of our difference. So basically, while realizing this part is nothing but operational transconductance amplifier, OTA, or basically a transconductor, and it has its value of transconductance, which is omega u, and same current like the way we derived here. This current will be generated based on the signs of the terminals. Either the current generated will flow out or flow in, depends on the signs of the terminals. So basically our V out comes out to be Gm by C integral difference. So now in negative feedback loop, um, we discussed why we need a buffer to isolate the current and make it flow through a capacitor. So our V out will remain the same, where the correspondence where we discussed the negative feedback loop was omega u times the difference. So basically our omega u comes out to be Gm by C of this whole amplifier or negative feedback loop. So there are several possibilities in this structure which will give us a delay. So what are those? So basically we are having a voltage buffer, right? So ideally the transfer function is 1, but in reality the transfer function is basically 1 plus the contribution of zeros and the contribution of poles, and as we know, poles and zeros both introduces delays. So basically, it's not ideally 1, but it's something less than 1, or not, let's not say less than 1, but introduces a delay. Along with that, this OTA also introduces a delay because it also has the parasitic effect. And there are parasitic capacitance from every node of the circuit to ground. So basically, let's say like from this node of the circuit, from this node of the circuit. So we will be having parasitic capacitances from every node of the circuit to ground. So also we have a resistive voltage divider. So the resistive voltage divider will also give us a parasitic effect. So let's discuss parasitics with voltage divider. So we have our voltage divider over here, and we have supposed the same values where uh, we have had in this structure. So at this point, by looking at this resistive structure, we can say that at this point we will be getting V naught by K as the voltage. But ideally, non-ideally, there exists a parasitic capacitance, and therefore, at this point, it's not right to say that we are getting V naught by K, but the voltage at this point will be basically V naught times the parasitic effect, and which basically has derived here. So we can pause and see over here. So this is the parasitic effect. This is nothing but the impedance division and voltage divider, and where we have considered impedance due to resistor, basically resistance, and the impedance due to capacitor in parallel, and that's how we have derived this. And by rewriting this in the analog template, we can arrive to this equation where we have our DC gain, and not DC gain basically, but at DC, when we equate S equals to 0, basically J omega and omega equals to 0 at DC, we get V naught by K as output. And in this case, the pole is at this value. So that's how we do the sanity check as well. So like this is the way the pole like parasitics act with voltage divider as well. And along with voltage divider, basically like we included this capacitor, but this there is also a parasitic capacitance which can cause a zero, which is connected with the VCC, let's say. So yeah, so we have talked or discussed as of now the probability of having the parasitics in the circuit, and which will introduce a delay. So while modeling the delay due to parasitics, there are extra poles and zeros, and they can be in any part of the system. So let's say we model the delay in this way, where we have the effect due to poles and zeros. And while modeling, let's consider a negative feedback amplifier with an extra pole in forward path. So that's how we model delay. And let's say we have extra pole P2. Why not P1? So basically the first pole is very near to the, let's say, not origin, but origin of the body block due to the integrator. So let's say we have a pole and we have a parasitic due to this pole, 1 by 1 plus S by P2. And when we derive an equation for the system, so we have our difference over here, and the transfer function basically is this, which is this is contribution from integrator, and this is contribution due to the delay introduced by pole, is nothing but basically our output. And when we rewrite this equation, we arrive to the equation somewhat in the form of V naught by Vi, and which is basically when we write in an analog template, so which gives us a DC gain of K when S equals to 0. Thus we can make a sanity check over here as well. So our transfer function comes out somewhat like this, like exactly like this. So this is how we rewrite the equation, where we say that this is our second order equation, and we have a standard second order denominator of the standard equation, from which we can find the natural frequency and damping factor. So we have written this equation in that format only, basically rewritten the equation from here, so that we can compare and find out the natural frequency and damping factor. So the natural frequency omega n, by comparing to the standard denominator of standard equation, comes out to be this value, under root omega u times P2 by K. And our damping factor comes out to be half under root P2 by omega u by K. And we know if the damping factor is very, very greater than 1, then the step response looks as of a first order system. And if the damping factor is basically exactly equal to 1, then there will be a sinusoidal ringing in the step response. And for very, very less equals to 1, let's say we have a clean without overshoot response. So basically what we'll say is we have our damping factor very, very greater than 1, which we will call overdamp system, and the response of that system is like this. At the boundary condition where damping factor is 1, we will call it as a critical damped, where it is most likely to be with a delay of 1 by E. And we have underdamped system, which will cause oscillations. And the desired response is usually critically damped or slightly underdamped while making an or designing an op-amp. So let's say we want critically damped system. So basically we want our value equals to 1, and basically we want this value to be equal to 1. So when we put the value of our damping factor as 1, and we know our damping factor basically arrives or comes from this value, and along with that we have to consider that the TD is equals to 1 upon E times K by omega u when the damping factor is exactly equal to 1, and that's what a critical case is. So basically from this equation we get the value of P2 as 4 times omega u by k, and thus we set a lower boundary or a lower limit to the location of P2. And we also know if damping factor is very less than 1, we will get underdamped response. So basically, when P2 is very lesser than the frequency of this, we will get severely underdamped response. And as we know, the denominator of transfer function will always give the poles in the left half plane. The system is basically unconditionally stable for any value of P2. But if P2 is very less than this value, we will get a severe underdamping. So I think that's about the time delay introduced due to the parasitics. And that's all for this video. Thank you so much.